I want to talk about this categorification program that's at the root of unity, which is a relatively explicit construction of some quantum invariants of 3 and 4 manifolds. That's our motivation, but uses some combinatorial or representation theoretical techniques that I will try to sketch out in relative detail. All right, so the whole story of what we want to do fits in the background of topological quantum field theories. So this is the physicsy part. So you should treat this part as a philosophical background. So topological quantum field theories, as everybody probably have heard from, this is defined by Atiyah and Siegel in the 1980s. As an axiomatic way of understanding work of Donaldson, Wheaton, and people, etc. So this is formulated in the following way. So this is an overly simplified version, understanding of the actual quantum field theory. So what does topological quantum field theory do? Topological quantum field theory studies the evolution of our quantum worlds. So imagine this is M0 or M1, these are our worlds, the three-dimensional world. As it evolves in space-time, the trajectory will be a four-dimensional manifold. Okay, so in physics, quantum field theory, you assign to our world some Hilbert space of quantum states, and how the quantum states changes is, we have a board so we can roughly think. So in quantum mechanics, you know that in quantum mechanics, your quantum states changes according to Schrodinger's equation. So this is a differential version of it. So roughly speaking, you can make sense of how this psi t changes. This is how the quantum states changes with respect to time is e to the I h bar minus I h bar h hat. So roughly written in this integral version. Well, topological quantum field theory is the theory where h hat, you have no Hamiltonian, is identical to 0. So unless your world goes through some drastic topological changes, these quantum states will not change. Okay, so drastic topological changes means maybe some new world is given birth to by some black hole explosion, or stars are merged, things like that. Okay. All right. This assignment of Hilbert spaces to our world sheets must satisfy some coherence axioms. So topologically, when you wiggle these manifolds and a little bit, this data does not change. So you can try to formulate the axioms by yourself, and those are the natural conditions to impose, as done by Atiyah and Siegel. This okay? So topological quantum field theories is a very convenient language to package a lot of topological invariants studied by various people. So in dimension 1 and 2, this is essentially a combinatorial problem, and you can leave it as an exercise for interested people to work on. For instance, in dimension 2, to give you a topological quantum field theory, so you just assign a vector space to one-dimensional manifolds. In this case, it's just a disjoint union of circles, and how it evolves in space-time, it's very easy. To a circle, you must assign a commutative Frobenius algebra. So you can try to figure out the coherence axioms in this case. But in dimension 3, this becomes very interesting. The first example is constructed by Jones. So this the celebrated Jones polynomial associated to knots and links embedded in three-dimensional Euclidean space, or S3. And Wheaton used the Chern-Simons theory to give a physical explanation of Jones' construction. And later, this construction was generalized by rethinking to RF rewrote to much more general context using representation theory of quantum groups at roots of unity. And there are various variants of Witten-Rashtinkin's construction known as Kuperberg or Henning or Kaufman invariants of three manifolds. So so in essence, there is a huge family of examples in dimension 3 given by representation theory of quantum groups. Okay? Any questions? But in dimension 4, the story is much more sporadic. So in dimension 4, this is two Fields medalists' work building. It came from Donaldson-Floer homology theory, or later Seiberg-Witten theory. So they constructed topological field theories in dimension 4. And notice that in dimension 4, this is much more sophisticated. Nothing is combinatorial. Everything is depending on gauge theory, using hardcore elliptic PDEs, solving elliptic PDE as to find the solution spaces will give you invariants when you package them in the correct way. Is this all right? So it's much more complicated than three-dimensional case. So therefore, it's a very natural question from in hindsight these days. When Igor Frankl posed this question with Louis Crane, that how are these different dimensions related to each other? So they started observing this from a very simple example. So Donaldson-Floer homology theory, or Donaldson theory, behaves very much like Kuperberg's Y.Qi SO3 plus, the Borel part of SO3, SO2 invariant for associated with the three manifold. So functorial, they have some similar behavior. And we have seen that Kuperberg's invariant is a close relative of Witten-Rashtinkin-Turayev 3D TQFT associated to the Drinfeld double of this Hopf algebra. So it's the quantum group Y.Qi SO2. So they conjectured that, well, if these stories are completely combinatorial. So if you can lift this story to a four-dimensional theory via the so-called categorification process, maybe you can give a combinatorial description of Donaldson's construction and eventually help you compute what these invariants are for arbitrary four manifolds. For instance, this is not even known for arbitrary. A Donaldson theory is essentially computed for some very specific Khovanov varieties in dimension 2, but it's not known for arbitrary four manifolds. Okay? All right, here a caveat is that Q has to be a primitive nth root of unity, so that this input data of Y.Qi SO2 are finite dimensional Hopf algebras, which we'll discuss later. Any questions? Well, when Igor Frankl first raised this conjecture, even Witten didn't believe that this process could be carried out. And amazingly, a few years after he formulated this conjecture, some direct evidence came into existence. The first significant evidence was the construction of Khovanov homology and its generalizations. So what is Khovanov homology? Khovanov homology is, roughly speaking, a categorification of the Jones polynomial. So it's a functorial link invariant. So it associates a bigraded chain complex or its homology group to a link, and it's an invariant of the corresponding underlying link. And it's functorial in the sense that I will explain later in terms of topological quantum field theory. And secondly, there is the combinatorization of Seiberg-Witten theory done by Osvas and Zabel. They coined the terminology Hegar-Floer homology. So if you start with a four manifold, a three manifold, you can decompose it. You can describe it in terms of the combinatorial data of the Hegar diagram and use the Hegar diagram to give you a description of the corresponding Seiberg-Witten theory. So this is And it's not only gives you a categorical three-manifold invariant, it gives you knots link invariant satisfying functoriality, so which is a very strong invariant. This okay? And for many cases are quite computable because it's combinatorial in nature. This okay? So what is this functoriality? This is the extra dividend part. Functoriality means the following. This is because the whole theory is part of the topological quantum field theory. So if you have a knot and link sitting inside R3 or S3, as your R3 or S3 evolve in time, the trajectory of this link will sweep out in time a two-dimensional surface. So it's going to be a surface with boundary, where the boundary parts are boundary is this given knots and link. So Khovanov homology or Hegar-Floer homology theory assigns to this entire datum this to knots and links. It assigns this bigraded chain complex or its homology groups, and to this surface it assigns a map of this corresponding bigraded chain complex or their homology groups. So these are chain complexes. When you take Euler characteristics, you get some polynomial. You recover once you pass to the Euler characteristic level. You recover the Jones polynomial or the celebrated Alexander polynomial, but this is the Hegar-Floer homology of the knot, whose Euler characteristic is the Alexander polynomial. So in this sense, this homology theories categorify the Jones or Alexander polynomial. However, when you pass to the Euler characteristic level, this data assigned to the surface S is just completely forgotten. You don't have this data. This okay? Any questions? All right. So now I want to digress a little bit and go into the most basic categorification in the story. So I want to describe why, first off, these chain complexes or graded chain complexes are so essential in these constructions. So to do this, let's digress a little bit into very basic homological algebra. I know there are some graduate students in here, so please bear with me that this is very, very basic. And if you fall asleep, I don't blame you, but I'll remind you to wake up at some point. Yeah. A previous page? A dotted arrow just means it doesn't exist on this level. It's forgotten. Okay. No arrow. Yeah, no arrow. Should have put a red cross there or something. All right. So what is homological algebra? I'll give you a biased review of what homological algebra studies and how it's used in categorification. So this is my personal philosophical understanding. So it's a little bit biased. So to do this, let's work over a field for simplicity. So homological algebra is the study of chain complexes. So it's a graded vector space over a field equipped with a differential operator, d, such that d squared equals 0. Right? So when you have a graded vector space, graded over z, and d squared equals 0, you can discuss its corresponding homology or cohomology. So this is kernel of d, quotient image of d. And this is the familiar construction. So, well, my biased understanding of homological algebra is what can you do with this? What operations can you do on the basic objects of homological algebra on chain complexes? Well, the first basic operation you can do is you can form the direct sum of chain complexes, and that gives you another chain complex. Okay, so it's very obvious that this is still a chain complex because the differential operator acts component-wise. And slightly less trivial is the fact that if you have two chain complexes, you can form their tensor product, and it still forms a chain complex. Okay, so this tensor product is the differential operator now acts according to the Leibniz rule, a super Leibniz rule, if you want, where when you pass through a homogeneous component of degree k, you just insert a sign of -1 to the degree of k. Secret is k times 1, where 1 is a degree of the differential operator. Okay? So even slightly less non-trivial is the fact that there is an internal Hom between chain complex. So there is internal Hom that's adjoint to the forming tensor product. So what this means is you can form the vector space homomorphism space from one graded vector space to another, and consider all shifted vector space homomorphisms, and put a chain complex structure on this shifted homomorphism space as follows. So the differential acting on the linear map F applied to some element of k. Well, this is the formula that d of fk minus 1 to the degree. When you commute f and d, you pick up this natural sign. Okay? And when you take homology of this chain complex, it gives you this computes the homomorphism space in the homotopy category of chain complexes. Okay? How big chain complexes are in the homotopy category. So I'll sweep the rest of the standard homological algebra lessons into the part 4 under the rug. So this is the triangulated structure that's defined by Grothendieck and Verdier. So there are homological shifts, and if you have a map of chain complexes, there are cones of these maps. So if you have a short exact sequence of chain complexes that lead to a distinguished triangle satisfying axioms TR1 through TR4, etc., etc. Okay, so I'll sweep the rest under the rug. But why is this construction so fundamental in categorification, or more generally in mathematics and theoretical physics? So my best reason is homological algebra is a categorification of the abelian group Z. Why is this? So the objects, or homological algebra, you can think of this as the study of chain complexes. Before modeling out homotopy, when you quotient out homotopy, or things that are homotopy equivalent to each other, there is a well-defined Euler characteristic assigned to chain complexes. So you take the alternating sum of the dimensions of the homology. Maybe I should have put some boundedness condition, but so we're studying finite dimensional graded vector spaces. So let's pretend that this is well-defined. And so if you have a direct sum of chain complexes, the Euler numbers just add up. When you have a tensor product of chain complexes, the Euler numbers just multiply together, and the homological shift is just multiplication by -1. So this is an isomorphism from the this taking Euler characteristic is well, in today's more modern language, this is the Grothendieck group of this triangulated category is just Z. This okay? So there's a more a variant of this construction. Well, we can consider graded vector spaces, so this degree is orthogonal to the homological degree, and so the homological differentials are expected to respect this extra degree. So you can take graded Euler characteristic, and so in this way, this gives you a categorification of this ZQQ inverse, or what people say quantum integers. But what you gain is you get an extra gradient shift functor, which corresponds to multiplication by Q in here. So in representation theory, people like to consider graded vector spaces, just as in Michel's talk. Corresponds to considering some C-star equivariant structure, so that things become easier in representation theory. Is this okay? All right. So, well, the features we have seen from the usual homological algebra 1 through 3, you can form direct sum, you can form tensor product, inner Homs. Well, many of you have taken a basic course in representation theory of finite groups. Well, you would recall that this features is something we have seen in another course, representation theory of finite groups. So we can generalize this. So representation theory of finite groups can be incorporated into the representation theory of Hopf algebras, the special case of Hopf algebra. So let's try to reformulate this in terms of representation theory. So what is a Hopf algebra? It's a generalization of group representation. So if you have a ground field, think of, if you're unfamiliar with the language, the Hopf algebra is just a generalization of the group algebra of a group. So a K-algebra is called a Hopf algebra if there's an algebra homomorphism called co-multiplication and co-unit map and the antipode generalizing. This is, if you have a group, this sends G to G tensor G, and this sends G to 1, and this S is sending G to G inverse, satisfying these Hopf axioms. So the co-multiplication is co-associative, and this epsilon is the co-unit of delta, and it satisfies this convolution identity. So this S is the convolution inverse of the identity map. Okay, so this is some basic axioms for Hopf algebra. I hope this is okay. So if you feel why these are the conditions to impose, feel confused, just think of H as the group algebra of a finite group. Then these are the natural conditions you have to impose.
The very last state one, but that's the other bracket.
What's that?
The left-hand side and right-hand side are the same.
Oh, yeah, S should be here. I'll correct the notes, and thank you. All right. So let's take the Hopf algebra. And if you have two modules over the Hopf algebra, well, the direct sum is always a module over the Hopf algebra. So this is more generally true. If you have any algebra, any two modules, the direct sum is a module. But the nice thing about Hopf algebra is that you can use the coproduct to define a tensor product structure on the tensor product representations. So if you have two H modules, the vector space tensor, well, in general, if H is not a Hopf algebra, just a normal algebra, this space carries an action of H tensor H. All right, but if you just want one copy of H to act on it, you have to have a homomorphism from H to H tensor H. And if you want this tensor product to be associative, then that's the axiom we imposed earlier. So therefore, this this becomes another H module where the H acts this acts according to the co-multiplication on H on each component. Okay. So similarly, if you have two H modules, the vector space homomorphism or the inner space homomorphisms. So I use capital Hom to denote this is all linear maps from K to L carries an H module structure using the antipode construction. This is one particular choice of action that makes things nicer. Some formulas nicer later, but there are two ways to define this action, but they're related by some isomorphism. Is this okay? All right. So, what are some natural examples? Well, if H is the group algebra of a finite group, or can be infinite as well, the co-multiplication, as I've described, is G tensor G. Delta sends G to G tensor G, and epsilon evaluates at G equals 1, and S of G is G inverse. So this is a Hopf algebra, and Another natural source of Hopf algebra comes from compact Lie groups. So if you have a compact Lie group, the cohomology ring of the compact Lie group is a Hopf superalgebra. Well, the name Hopf algebra is actually a misnomer because the first non-group algebra Hopf algebra discovered by Hopf was this case cohomology ring of a compact Lie group, and this is actually Hopf superalgebra in this case. So for instance, if G is a compact Lie group UN, you can just take the Hopf algebra of a cohomology ring of UN is generated by odd super differentials d1 through dn, where each of these di's is of degree 2i minus 1. Okay, and how is the Hopf algebra structure given? So it's these di's are like super differentials. So delta of d is di tensor 1 plus 1 tensor di, and epsilon kills di's, and the antipode sends di to minus di. Okay, so I was trained as a representation theorist. So another natural source of Hopf algebras appearing in representation theory was from a Lie algebra. So if you have a Lie algebra, you can form the universal envelope algebra of this Lie algebra. So it's a tensor algebra quotient relations coming from the algebra relations, Lie bracket. So this is the Hopf algebra by setting delta of x to be x tensor 1 plus 1 tensor x, and epsilon kills x, and s sends x to negative of x. Is this okay? So you can check that the modules over this Hopf algebra is equivalent to representations over this Lie algebra. So that's why people like to study Hopf algebras. Any questions? All right. So using this language, let's try to reinterpret homological algebra in terms of representation theory. So it's homological algebra is nothing but the representation theory of a very simple Lie algebra, a very simple Hopf algebra, which is the cohomology ring of S1, or the Hopf superalgebra of KD over D squared. So this is S1 is the group U1. So this is just we're studying graded modules over this graded superalgebra, KD over D squared. Right? So the basic objects are the same. So what about the other features? So are the other features of homological algebra present for arbitrary H modules? So these are natural questions you can ask yourself. So for instance, what's taking cohomology for an arbitrary H module instead of this particular case? What are the triangulated structures involved for H modules? So this is, well, a priori, this is an abelian category. How do you see a triangulated category coming from this abelian category? Well, to answer these questions, let's revisit how you pass from how we reinterpret this representation theory of this very small Hopf algebra of dual numbers, reinterpret homological algebra as the representation theory of this small Hopf algebra. Well, so what is taking cohomology for this very small Hopf algebra? Well, a chain complex, as we have seen, is just a graded module over this two-dimensional Hopf algebra KD over D squared. So if you have taken linear algebra course, you know that modules over KD over D squared are very easy to understand. It's the easiest case of a Jordan canonical form, right? Where the Jordan block can be at most 2. So therefore, any graded module over this decomposes into a direct sum of either simple modules up to grading shifts, and this where Jordan block is size 2 case. So this is a two-dimensional module where D sends this copy of K to that copy of K. So we write this as multiplication by 1. Okay? Well, what does taking cohomology do? Taking cohomology just is a systematic way of killing this second type of factors. So taking cohomology is just a functorial way of eliminating this second type of so-called contractible subcomplexes. So what's special about this subcomplex? This subcomplex is of course just a projective KD over D squared module. It's isomorphic to this as a left module, but slightly less obvious is the fact that this is also an injective module. So such modules are also injective. Well, this is essential because this algebra is the cohomology ring of S1. S1 has Poincare duality, so it you can use Poincare duality to show that the projective dual is the duals of projectives are always injectives, so the dual of projective is isomorphic to itself in this case, so therefore they're also injective. This okay? A quick explanation. So this is more generally true for cohomology ring of compact Lie groups. So a natural question now to rephrase the earlier question. So the questions now become: when are projective H modules the same as injective H modules? What conditions do we have to impose on the Hopf algebra H so that this condition holds? And secondly, when projectives are the same as injectives, how do we systematically kill them or in a functorial way? This okay? So to do this, I have to quote this classical theorem of Larson and Swidler that goes back to the 1960s that answers the first question. So if H is a Hopf algebra, then H is a so-called Frobenius algebra if and only if H is a finite dimensional Hopf algebra. So Frobenius really means literally, Frobenius implies that the projectives and the injectives are the same. So in particular, for finite dimensional Hopf algebras, projective H modules coincide with injective H modules. Okay, so this is not a coincidence for KD over D squared, projectives or injectives. This is because KD over D squared is a special case of Larson and Swidler's theorem. This okay? All right, so now let's try to answer using this construction of Larson and Swidler. Let's answer the second question. How do we functorially kill projective injective objects? Yeah. Sorry, come again? Yeah, on H modules, yes. Yeah. Or the Frobenius structure is really defined in terms of there's a non-degenerate pairing from H to the ground field that is that can be that can be used to play the same trick I said earlier, to turn projectives into injectives and vice versa. All right, so now let's come to the definition of the stable category. So our goal is now let's focus on the finite dimensional Hopf algebra, which is Frobenius. We want to systematically kill projective and injective objects in H representations. So when I was a student, the first lesson I learned in categorical constructions is, well, if you want to kill something, you just throw them out. But it turns out this is a really bad way of doing it. So the definition of doing such categorical quotient is categorical killing some object is formally categorical quotient. So this is the stable category of H representations or H modules has the same objects as H mod. So you never tamper with objects. What you want to do is you kill morphisms that factor through the objects you want to kill. So how do you measure morphism spaces in the quotient category? So the homomorphism space from a H module K to L in this quotient category is you take the usual H intertwining maps from K to L and mod out all those maps that factor through a projective injective object. Okay, so this is a natural construction, but what's nice about this construction is that classical theorem of Heller tells you that whenever you have a Frobenius algebra, where finite dimensional Hopf algebras are examples of this case? Previous page? Here from K to L, denominator. So these are maps that goes from K to L that factors through projective injective objects. So these maps that can be written as a composition. Sorry for this. Okay. So what's nice about this is this Heller's theorem is that whenever you have a Frobenius algebra, this category is naturally triangulated. So it has the same structure as the homotopic category of chain complexes as we have seen. If you have a short exact sequence of H modules that gives you a distinguished triangle in the quotient category and satisfying TR1 through TR4, etc., etc. Okay, so this construction is really a natural generalization of taking cohomology. So cohomology of the usual Hopf algebra KD over D squared lives over the stable category of that small, very small Hopf algebra KD over dual numbers. So because there are many graduate students here, so I'll try to be more precise. I'll give you a sketch how this is constructed. So what are the shift functors on this category? So this is slightly different from what you have seen in algebraic geometry, how you shift chain complexes. It's a little bit counterintuitive. So if you have an arbitrary H module, you choose an injective embedding or a projective cover of this module into an injective object, or this is the projective cover of this object, then declare that homological shift to be shifted by 1 is the co-kernel of alpha, and minus 1 is kernel of beta. And you can check that whenever H is a Frobenius algebra, this construction is well defined, independent of choices of injective embedding or projective covering map, and they're inverse of each other, these two functors. And what are distinguished triangles? Distinguished triangles come from as follows. So if you have a map between, so part of the TR1 through TR4 is whenever you see a map between objects in a category, they fit into a distinguished triangle. And how do you construct that? So if you have a map from K to L in the quotient category, of course, this is represented by some actual H module homomorphism, and you just choose an embedding of K into an injective object, and you naturally have this F, and then you form the push-out diagram of this map. So this push-out can be thought of more concretely. This is just the direct sum of IK with L, quotient the image of K under F and this natural embedding map. So this is the cone. So you can, the push-out satisfies that the co-kernels are canonically identified. So these are, by our definition, this is K1. So now you declare this part of the diagram to be a standard distinguished triangle. So this is a distinguished triangle. Any triangle isomorphic to a standard distinguished triangle is called a distinguished triangle, and verify the axioms TR1 through TR4. And it's not very hard. So I'll leave you as the rest as exercises. Okay? So this construction is the so-called stable category construction. And these days it has played a very big role in the study of tensor triangulated geometry by Balmer and many people. But I don't think everybody is familiar with this, so I gave you the most basic description here. All right, so as in categorification, so in modern days, when you try to do categorification, or this is really a basic philosophical question, if you want to understand a category, the most basic objects to understand are not objects in the category, but instead morphisms. How do you compute homomorphism space in this category? So categories are really characterized by morphisms. So to answer this question, how do we compute a homomorphism space in the stable category? I have to resort to this so-called integral element. So an element is called called an integral in H. Essentially, that means the element spans a trivial representation in the left regular representation of H acting on itself. So H acts on itself by left multiplication. So if you can find a trivial subrepresentation sitting inside there, then a basis element is called a left integral. Okay? So part of the Larson-Schwitters theorem translates into the following statement. It's equivalent to that this H is being Frobenius, is that whenever you have a finite dimensional Hopf algebra, the space of left integrals is one dimensional. So in particular, it's never empty. It has a non-zero element spanning a trivial one-dimensional subrepresentation inside the left regular representation. This okay? So let's look at some examples. Again, if you have a group algebra of a group, this is a finite dimensional Hopf algebra if and only if this is a finite group, G is finite group. And of course, you can see that what spans a trivial subrepresentation inside the left regular representation, you have to take the sum of all the elements, all the group elements. This makes sense if and only if this is a finite group, this element. And this is indeed an integral element because earlier, as we have said, epsilon applied to arbitrary element G is 1. So when you multiply this element by arbitrary G, just shift this elements around and doesn't change this element. Okay? So next, this is the graded Hopf superalgebra dual numbers, KD over D squared. Well, you can easily see that the integral is just spanned by the element 1, element D. Okay, this is because epsilon D is 0, as we have seen from the Hopf algebra structure. So more generally, if you have the cohomology ring of a compact Lie group, the top differential form, the hard measure on that Lie group is the integral. So that's why this element is called the integral in the Hopf algebra, because it plays a role of integration on compact Lie groups. That's where the name came from. Okay? So finally, let me describe to you a Hopf algebra that coming from Lie algebra. So if you form the one-dimensional abelian Lie algebra with D, such that delta of D is D tensor 1 plus 1 tensor D, and in characteristic P, you can form a very nice quotient by the ideal general derivative D to the pth power. So this is a graded Hopf algebra if characteristic K equals P. Okay? So using this integral element, we can measure how big the morphism space is in the stable category. I was surprised that this formula was never discussed before in the literature. Seems to be pretty basic. So if you have two H representations in H module, how big is the homomorphism space in the stable category? So first you take the space of H invariants in the inner Hom and quotient this integral operator applied to this inner Hom space. Okay, because of the definition of integral, we have seen that this space is going to be a subspace inside H invariants because H acts on epsilon on lambda by epsilon homomorphism. So therefore, the denominator is a subspace of the numerator, so you can form this quotient. Is this okay? Yeah. This is the vector space homomorphism from K to L, and we defined an H action on this. So you're just taking the invariant part under that H action. So H acts, maybe I should have said H, if you have an H module, H invariants are those elements H acting on M equals epsilon of H times M. Come again? This one? Denominator? Yeah, this is the integral element. Yeah, this is actually H intertwining maps from K to L.
Numerator column is H modulo map.
Yeah, the numerator is H modulo maps. No, this is, sorry. This is the inner space homomorphism. These are all K-linear maps from K to L. When you take H invariants, that actually the denominator, numerator coincides with H intertwining maps from K to L. This okay?
Why is numerator inside the numerator?
This is because, do we have any eraser? Sorry. Oh, yeah. This is because of the definition of lambda, that H acts on lambda is epsilon of H lambda. So if you have lambda acting on some F, then H acting on it will be the same as H acting on lambda times F. So that's epsilon of H. Is this okay? All right. So writing it this way is a little bit weird, but this is just to emphasize inner harm is quite important in the story. So again, this is there are so many graduate students. I'll try to explain how you prove this in a few basic steps. So first off, the denominator is nothing mysterious. These are just H intertwining maps from M to, sorry, K to L. Another typo, didn't correct. Okay, why this is the case? So if you let's look at both inclusions. So if you have an H intertwining map, how does H act on this as a linear map? We have written down the formula before. This is H2 composed with F, composed with S inverse applied to H1. But remember, this guy is H linear. So F is H linear, so you can pull this element out. So when you pull this out, the Hopf-algebra axioms earlier tells you that this is just epsilon of H. So this is indeed an invariant under H action. And conversely, if you have an invariant under H action, you want to show that it's H linear. So this is some standard Hopf-algebra technique. You can just apply a co-multiplication and evaluation. So this is one of the Hopf-algebra axioms. Epsilon is a co-unit. And now you can split this element into H3 times S inverse H2. But forgetting this part, this is precisely the action. So this is H2 of H1 acting on F. Okay? So therefore, if this is F is an invariant, then this acts by epsilon of H1. So that's just gives you back the corresponding formula. Is this okay? So this is very basic, so, because there are so many graduate students. All right. So secondly, if you have a map that factors through a projective injective module, we try to make it more standard. So standardize this. What kind of maps factor through a projective injective object? A map factors through a projective injective object if it only factors through this canonical embedding of M into M tensor H. Okay. So sorry, I didn't say it earlier. H itself is projective injective objects, but because of tensor Hom adjunction, you can easily show that when you tensor a projective injective objects with arbitrary modules, it becomes still this is a projective injective object because tensor is left adjoint to Hom. The inner Hom we have written down. So therefore, this guy is still going to be an injective object. So therefore, there's the canonical embedding of M into M tensor H. On the second factor, you just put the integral here. So therefore, you have this. So any map that factors through a projective injective object must factor through this canonical embedding from M into M tensor H. And why this is the case? This is, well, it suffices to show for n itself is projective injective, and projective injective are summands of a direct sum of copies of H. So it suffices even to show when n equals H case. So if n equals H, you have this nice, very nice diagram. M factors, M embeds in M tensor H, and H in turn embeds into H tensor H. But H itself is injective, so this embedding splits out. So there is a splitting, so therefore F must factors in this way. This okay? So very easy exercises. So finally, we want to characterize what are such maps that factors through this canonical embedding of M into M tensor H. This is the third lemma. And such maps are precisely what you have seen in the denominator. So these are all those maps that has the form. It's lambda applied to some linear map M from M into N. So this phi is not necessarily an H intertwining map, but when you apply lambda to it, it becomes H intertwining. This okay? Just as we have seen over here. And I'll just show you one-sided inclusion. This is very easy. So you have this canonical embedding of M into M tensor H. Then you just restrict this H intertwining map F tilde to this M tensor 1 sitting inside here. And this is no longer an H intertwining map because you're restricting to not a subrepresentation. M tensor 1 is not a subrepresentation in M tensor H, but M tensor lambda is. So you restrict this map to here, then you can easily verify that lambda applied to phi is indeed the map you wanted. So lambda applied to phi is the desired map. Okay. So the converse is also similarly easy. I'll leave you as an exercise to check it. Is this okay? I hope I've given you enough exercises because this is supposed to be for graduate students at the first lecture. All right, so let's continue the discussion of this examples we have seen from earlier. So if you have the Hopf algebra of finite group, in this case we have seen the integral is summation of all group elements inside G, and we know a classical theorem. Well, let's try to use what we have seen from the previous theorem, how to measure morphism space to deduce some classical results. So for instance, a classical result of Y.Qi says that the group algebra is semisimple, or representation theory of G is semisimple if and only if the order of G is invertible in K. And why this is the case? So this object, this category is semisimple if and only if the trivial representation is actually projective injective. This is, as we have seen, if you have a projective injective object, when you tensor with arbitrary objects, it will become projective injective. So if you have trivial representation which is projective injective, then any representation is isomorphic to the trivial representation tensor with itself. So therefore, any object will be projective injective. And trivial representation is projective injective if and only if the morphism space in the stable category from this representation to itself is 0 by our construction. And how do you measure the morphism space? Earlier we have seen you take inner Hom, so this vector space homomorphism from K to K. This is just a fancy way of writing K itself, just one-dimensional vector space K with trivial H action. But now the denominator is lambda applied to this one-dimensional vector space. So this is, remember lambda is just summation of all group elements. So you're just quotienting K by the rescaled copy of K. And this rescaled copy of K is non-zero if and only if G is invertible in here. This okay? So this recovers the classical Y.Qi theorem. Secondly, if you have the graded Hopf superalgebra of dual numbers, KD over D squared, what are H intertwining maps in the denominator? Denominator are all those maps, because D acts by, according to the formula we wrote down earlier, a map is H intertwining if super commutes with the generating generator of this Hopf algebra D. And if it's in the quote denominator, if and only if it's lambda applied to some linear map H. So in that case, if you pick H to be homogeneous, this is the supercommutator of D and H. So this is precisely the chain maps up to homotopy equivalent. So this is the stable category is exactly the homotopy category of chain complexes. Okay, with the standard distinguished standard triangulated category structure. And finally, for this very nice Hopf algebra KD over D to the pth power, you have a very similar story as above, which I'll leave you as an easy exercise to check. The numerator comes from all H intertwining maps, or in this case, just maps that commute with D, and denominator are all those maps that are of the form lambda applied to some linear map, and in this case, use the Fermat's-Little theorem. You can show that this is the same as summation of D to the I composed with H composed with D to the P minus 1 minus I in characteristic P. So this is, all right. So for this reason, we call H modules modules over this very small Hopf algebra P complexes. So these are graded vector spaces equipped with a nilpotent operator D, such that D to the power is 0. And when you pass to the stable category, this is the homotopy category of P complexes. And the reason why we care about this is because of a very simple observation in parallel to the usual homological algebra by Bernstein and Khovanov. So this category is not only a triangulated category, it inherits the tensor product structure from the Hopf algebra H. And the tensor products are exact, so it descends to the stable category. And in this case, the Grothendieck group is not Z anymore. It's just, this is, you have taken graded modules over this ring. So they're iterated cones of the simple module. This is a local Hopf algebra. So therefore, any module is just an extension of the trivial module. And what you killed out is our projective modules. The projective modules have its Euler characteristic equal to the cyclotomic ring of a pth root of unity. So therefore, you recover the Grothendieck ring of this tensor triangulated category is OP. And again, the direct sum tensor product homological shift grading shift becomes multiplication, addition multiplication, and multiplication by -1 and multiplication by a primitive root of unity Q in this story. This okay? Oh, sorry, OP, I should have defined it in the slides. Maybe I'll send you the corrected slides after the lecture. So OP is ZQ quotient, the character of the free module, 1 plus Q. So this is the cyclotomic ring. Of a primitive pth root of unity. So the denominator is the cyclotomic polynomial of order P. This okay? Yeah, to be more precise, this is spanned by the trivial representation, and this guy is the character of 1 plus Q plus P minus 1 is the character of H. So this is just the graded shifts of copies of H. So in this quotient category, you have killed the free module H. So therefore, the Grothendieck group is just, well, you just really killed this relation. Why is H equal to, H is as a module, this is K, D, K times 1 Okay, so this is p-dimensional, right? So this is, the character is 1 plus q times 1 plus q squared all the way to p minus 1. This okay? All right, so again, I'm already out of time, so maybe I should skip the proof. And next time we'll use this result to build up categorification of objects that live over OP, for instance, the quantum group at roots of unity.